This week's Interactive Advanced Concept Presentation 6 is on the nuclear bomb. To some extent, hydrogen and atomic bombs are the same because both types of bombs are categorized as nuclear weapons. To talk about the differences, we must first understand the basic concept. Nuclear bombs are weapons of mass destruction that use nuclear energy to create an explosion. This energy, in turn, is contained in atomic nuclei and is released during nuclear reactions and radioactive decay. If both types of bombs use nuclear energy, then what is the difference? We will see that later in this presentation. First, let's talk about the atomic bomb, or fission bombs. Usually, they look like an elongated, rounded torpedo. The main danger lies inside of them. To get the nuclear explosion, a certain reaction must occur. That reaction is the chain reaction of the fission of heavy nuclei. There are several heavy elements that are capable of such a reaction. Usually, uranium-235 is used in nuclear weapons. Uranium has at least two different isotopes, 238 and 234, but only uranium-235 can produce a nuclear weapon. To maintain the maximum amount of energy during the explosion of an atomic bomb, the content of the 235 isotope in uranium should be at least 80%. You can also create a plutonium bomb, which will be based on the isotope with the number 239. However, this element is rarely found in nature, which means that you have to create it artificially. So the principle of atomic bombs are atomic bombs rely on nuclear fission, where heavy nuclei such as uranium-235 or plutonium-239 split into smaller nuclei, releasing a tremendous amount of energy. The process includes initiation, chain reaction, and critical mass. For the initiation, a neutron initiates the fission process by colliding with a heavy nucleus. The chain reaction is each fission event releases more neutrons, which further induce fission in other nuclei, resulting in a self-sustaining chain reaction. The minimum amount of fissile material needed to maintain a chain reaction is the critical mass. The different components equal the fissile material, which is the uranium-235 or the plutonium-239, a neutron reflector, which reflects escaping neutrons back into the fissile material to sustain the chain reaction, and the explosive lenses, which are high explosives arranged to compress the fissile material into a supercritical state. For launching the weapon, the nuclear explosion occurs because a certain mass of fissile material is concentrated in one place. This can also be called critical mass. When it is reached, a nuclear decay reaction is formed with the release of energy. But for a powerful explosion, one critical mass is not enough. To get a truly destructive bomb, you need 4 to 5 critical masses of matter. There are several ways to achieve this, but the main one is implosive. Let's talk about the implosive. Imagine a nuclear bomb in the form of a small ball. Inside it are all the necessary components for a nuclear reaction, but the critical mass hasn't been reached. Suppose an explosive is put on the outside of a bomb and detonated. When properly exposed, the space inside the bomb will begin to shrink towards the center of the shock wave. The density of uranium or plutonium inside will increase and a nuclear explosive will occur. Here's the fission reaction, which is uranium-235 plus a neutron leads to krypton-92 plus barium-141 plus 3 neutrons plus energy. So now let's talk about the hydrogen bomb or fusion bombs. Energy is released due to thermonuclear fusion. A very fast explosive reaction takes place inside the charge with the help of elements such as deuterium or tritium. Other heavier elements can also be used along with them. However, the main effective substance is lithium hydride. By itself, it doesn't produce an explosion, so clearly it needs something else. And the detonation of this substance is usually carried out by an integrated nuclear device with low power called a detonator. When it is activated, energy is released, which triggers an explosive thermonuclear reaction inside the bomb. For hydrogen bombs, there's theoretically no limit to the power. So the principle is hydrogen bombs utilize nuclear fusion, where light nuclei such as deuterium and tritium fuse to form heavier nuclei, releasing energy. The process has a primary stage and a secondary stage. A fission bomb is detonated to provide the high temperature and pressure needed to start fusion. And the secondary stage is the fusion of those two elements occurs, releasing an immense amount of energy. Its components are the fission primary, which acts as a trigger for the fusion reaction, fusion fuel, which are those two elements, and radiation case. It contains and directs the energy from the primary stage to compress the fusion fuel. And here's the fusion reaction. Two elements go to helium-4 plus a neutron plus energy. Here are some facts. In the case of nuclear weapons, they're measured in TNT equivalent. Why? Because it is an explosive and quite well known. And to understand the power of a nuclear explosion, a certain amount of TNT is needed to produce the same energy, usually expressed in kilotons and megatons. So we have some examples of bombs. We have the Tsar Bomba, which is related to a thermonuclear bomb. It's a hydrogen type of weapon, and its power is 58.6 megatons. And then we have a Little Boy and Fat Man. Little Boy was dropped on the city of Hiroshima in 1945 and had a capacity of 13 to 18 kilotons of TNT. And then Fat Man destroyed the city of Nagasaki 3 days after Little Boy and had a capacity of 21 KT. The different consequences of strikes with such power is chaos, destruction caused by a shockwave, and radiation. There are 3 types of radiation. But alpha radiation will not do much harm. A person's clothing may protect them from contact with exposed skin. Beta radiation is a little more serious. It can cause significant damage at a distance of several tens of meters or feet from the radiation source. It could cause radiation burns or cataracts. And then gamma radiation. It is unlikely that anything will protect us from gamma radiation except for thick layers of certain substances such as lead and concrete. With its high penetrating power, it permeates the body, causing damage. Its most well-known consequences are radiation sickness, cancer, and gene mutations. Let's quickly connect the nuclear bomb to free energy and equilibrium of entropy that we learned in Module 4. Free energy, it determines the spontaneity of nuclear reactions. The large negative change in Gibbs and the large negative change in Gibbs free energy in nuclear fission and fusion indicates a highly spontaneous process. Its equilibrium is not typically achieved during the rapid processes in nuclear explosions, but is relevant in understanding nuclear stability. And for entropy, it increases significantly due to the massive release of energy and particles in nuclear reactions. These principles of thermodynamics and nuclear chemistry explain the immense energy release and the fundamental processes driving the operation of nuclear weapons. Thank you.